In this first video on Chapter 13, Vectors, we're going to first learn the algebra and calculus of vectors, and then we're going to have several applications of vectors to physical chemistry. So first, let's define what a vector is. We'll use the letter U with an arrow above it to designate a vector, and we're going to designate this vector in several different ways. First, we'll use its coordinate representation, U1, U2, U3, and we also want to have a geometric or a graphical representation. So let's put that on this graph here. So we've drawn on the X, Y, and Z axes in 3 space the coordinates, the X, Y, and Z coordinates of this vector U. So the X coordinate U1 is here on the X axis, the Y coordinate U2 is on the Y axis. We draw where that point would be, or where the coordinates U1 and U2 would be in the XY plane, and then we move up above that in the Z direction the distance U3 to get to the vector U1, U2, U3, which is defined as a directed line segment from the origin to a point. In this case, the point is in 3 space, U1, U2, U3. So from the origin to that point, and then we draw an arrow showing which way the vector is pointing, and that direction is from the origin to that point. The reason we want a vector to be a directed line segment is because we want it to use it to define physical entities such as force. So when we talk about a force, we want to know how strong it is. That would be the length of the vector, but we also want to know the direction in which the force is moving, and that's why we have a directed line segment. The same would apply for velocity. We want to know how fast it is, called the speed, but we want to know the direction in which we're moving, and this the same would apply for momentum. We want to know how strong that momentum is, but we also want to know the direction in which there is a momentum. So thus the need for a vector to be a directed line segment. The length of the line segment is called its magnitude, and the direction says in which way the force, velocity, momentum, etc. is being applied. So let's, on the next blackboard, look at what the length or magnitude of a vector is, how to calculate that. So we'll denote the length or the magnitude or the strength, which is probably the best word if we're talking about this physical entity like force, of a vector U. We use this notation kind of like an absolute value notation, but with a double set of vertical lines, and it's the sum of the squares of the components. So it's the distance from the origin to that endpoint. Notice also that we haven't mentioned this, but a vector the vector U could have just 2 components if it's in the XY plane, or it could actually have more than 3 components, as long as we understand that the 4th component doesn't necessarily correspond to anything, or doesn't correspond to anything geometrically. So this might be the X coordinate, Y coordinate, Z coordinate, and U4 might be the time of the vector, or the energy, or something like that. So that would if we had a vector of this type, we would have to generalize this definition to square U1, U2, U3, and U4. So on the next blackboard, let's actually calculate the length of a couple of vectors. So if the vector U is 2, -1, 3, then its length would be the sum of the squares of the components, square root of that, which would be square root of 14. If the vector V is minus 1, 2, minus 1, then the length or magnitude of v would be this, square root of 6. Now let's also define what happens when we add two vectors together, u plus v. That's a lot easier to show in the plane, so let's assume just to illustrate what it looks like if the vectors only have two components, but then we'll do an example when the vectors have three components. So when we add two vectors, in this case u, u1, u2, and v, v1, v2 together, what we do is we draw a parallel vector to the vector v, which is this vector over here, and a parallel vector to the vector u, which is this vector over here, and then we the sum vector is from the origin to the opposite end of the parallelogram here. So the question is, why does that make sense for that to be the sum vector? Notice that if the vector u1 has x value here and v1 had its x value here, then the sum of those two x values would be u1 plus v1, which would be here, which is where we have wound up in the sum vector for the x value. The vector u has this u value, or this y value, and the vector v has this y value, and when we add those together we get this y value. So this is v1 plus v2, and this is u1 plus u2. So you can see that a way to get to those coordinates is to extend, or to draw a parallel vector over here and a parallel vector over here, and then draw from the origin to that point. So if we generalize that to the sum of two vectors u1, or u and v, where u is u1, u2, u3, and v is v1, v2, v3, then we get the sum vector is u1 plus v1, comma, u2 plus v2, comma, u3 plus v3. So using u and v as above, the vector u plus v would be in the x coordinate 2 plus minus 1 or 1, minus 1 plus 2 or 1, and 3 plus minus 1 or 2. And the magnitude of the vector u plus v would just be to take the square root of the sum of those components squared, and so that'd be 1 squared plus 1 squared plus 2 squared, or square root of 6. On the next blackboard, we're going to talk about two types of products of vectors that have a number of applications to all the sciences, and we're going to show some of the applications to physical chemistry as well as some general applications. So first, let's start with what we call the dot product. So if we have a vector u and a vector v, we can dot them together, or take the dot product of these two vectors if we do this. If we multiply the u1 and the v1 component, and then add the u2 and the v2 component, and then add the product of the u3 and the v3 component. The reason that the dot product is important, however, is that when we take the dot product of two vectors, that turns out to be the norm of the vector u times the norm of the vector v times the cosine of the angle between the two vectors if we draw them in the plane, where this is the vector u and this is the vector v. then that angle theta is this angle right here. So one of the primary reasons we like the dot product is it allows us to get the angle between two vectors. So if we rewrite this, cosine theta is u dot v over norm u, norm v, length u, length v, and of course then theta would be cosine inverse of that. On the next blackboard, we're going to look at aspects of two vectors that are important called orthogonality. So two vectors u and v are said to be orthogonal if their dot product equals 0. Remember, dot product is the cosine inverse, so if we take the cosine of the angle and we get 0, that means the angles between them is 90 degrees. So let's note that that means theta equals 90 degrees between the two vectors. So let's look at these two vectors u and v, and let's first note that the norm of u is the square root of the square of these components, which would give us what? A third plus a third plus a third, or 1. So the norm of u is 1, and the norm of v is also 1 because it's the sum of, or the square root of the sum of the squares of its components are a sixth plus 4/6 plus 1/6 is 1. So its norm is 1. And it also turns out that u and v are orthogonal because if we take u dot v, we get u1 times v1, we get 1 over the square root of 18. If we take u2 times v2, we get minus 2 over the square root of 18. And u3 times v3 is 1 over the square root of 18. And we add those together to get 0. So since the dot product is 0, that means cosine of the angle between them is 0, and that means the angle is 90 degrees. So u and v are orthogonal. So u is orthogonal to v. On this blackboard, let's look at the second type of product we can take between two vectors called the cross product, written this way. And the cross product between two vectors is defined similarly to the dot product. It's the norm of u times the norm of v times, this time, the sine of theta, but we also need to put in a vector c, and c is, the vector c is perpendicular. So u has this definition here, and the c is defined as a vector perpendicular to the plane formed by u and v. So v is here and u is here, and they're both in the xy plane. Then the vector c would be perpendicular to that, or pointing in the z direction. The u and v vectors do not have to be in the xy plane, though, so we could have a different type of vector c like this. So the u and v could be here and here, and the perpendicular plane could be pointing sort of up and to the left rather than straight up, such as this vector c it right here is. I should note also that these definitions for u cross v and for u dot v, those can be derived. These geometric definitions can be derived, but they're very difficult to derive, probably a couple pages each for both of them. So let's just assume that we can start with them. Like the dot product, the cross product also has another way to be calculated that doesn't require that we know the angle between them, right? We can't use this definition for cross product unless we know the angle between them. So here's a way to calculate the cross product just knowing the starting vectors u and v on the next blackboard. To calculate the cross product, we form this matrix that has in the first row I, j, and k. We haven't defined I, j, and k before. They are respectively the unit vectors pointing in the x, y, and z direction. So I would be this, j would be this, right? They're unit vectors because they have length 1, and k would be this, 0, 0, 1, right? And when we do this calculation, it turns out to be a little bit complicated till you get used to it. Remember, u cross v is a vector, so we want to have an I, j, and a k component on it. So the I component turns out to be the product of these two minus these two. So let's put a plus sign on this and a minus sign on this. So the I component is found by using these four components which are not in the I column. So if we put that together, we get this. Now the J component, we have to actually start by putting a minus sign out here, and we do it the same way. So it's this, the product of these two, minus the product of these two. So that would be what? U1 V3 minus V1 U3. But remember, there's a minus sign out here. And we should also notice that when we look at these components, right, this and this are just reversed order, right? U2 V3, V2 U3, U1 V3, V1 U3. So for K, we go back to a plus sign, and that would be, right, U1 V2 minus V1 U2. And so this is U cross V, this vector here. Turns out that there's a little bit easier way to calculate this vector without writing so much. So let's designate that here. So let's first notice that the vector in coordinate form ABC is also the same as the vector AI plus BJ plus CK, because that would be the same as A times the vector I plus B times the vector J plus C times the vector K, which gives us back to this. So rather than write the I, J, or the vector, cross product vector with the I, J, and K components, we can instead just write the X component, or the first component, the second component, and the third component. And to calculate those components, if we just line up the vector U here and the vector V here, then this product minus this product is going to be the first component. The second component is this product minus this product, but remember there's a minus sign in front, so we get this. And then the last component is this product minus this product, so we get this. Get this result here. So those are two different ways, this way being a better way to calculate U cross V. What about some other significance of the cross product of two vectors? It turns out that U cross V equals, so actually this should be the norm of the vector U cross V. is defined to be the area of the parallelogram formed by U and V, so it would be the area of this parallelogram. And another geometric significance is that if we have three vectors in 3 space, u, v, and w, then the vector u dotted with the cross product of v and w turns out to be this. So u dot v cross w turns out to be the volume of the parallelepiped, that's this figure right here, formed by the vectors u, v, and w. On this blackboard, let's look at some vectors of the type that you will encounter in quantum mechanics. So first, the momentum vector, that should be familiar from physics. Momentum is mass times velocity, so the momentum is the vector p, and velocity is a vector, but mass is not. Another vector in quantum mechanics would be angular momentum. So if we define the position vector as r, then angular momentum L would be, or is defined as the cross product of the position and the momentum. And the force on a charge q, velocity v, which is a vector through a magnetic field of strength b, would be the force vector equals that charge q, which isn't a vector, times the cross product of the velocity, the charge at which the charge is moving, times, or cross, that is, with the magnetic field strength vector b. We have these 3 important vectors in quantum mechanics. So let's look now at some calculus on vectors. Let's suppose that the vector p is defined like this. So p has a p1, a p2, and a p3 component, but all of those components are functions of time. Then the derivative of the vector p with respect to t would be what you would guess. I hope you would guess correctly. It would be this p1 prime of t, comma p2 prime of t, comma p3 prime of t. And that could also be written this way. I'm sorry, that should be, we're defining the function f of x, y, z to have a gradient written like this with an upside down triangle in front of f to be partial f partial x times I plus partial f partial y times j plus partial f partial z times k. There are several important quantum mechanics entities that we need to find that involve the gradient, and they are these. So the flux of a solute is going to be minus d, where d is a diffusion constant, so minus d times the gradient of c, where c is the concentration of that solute as a function of x, y, z. So the flux of heat is also calculated using a gradient. It is the product of the thermal conductivity lambda times the gradient of the temperature, and notice that the temperature is a function of x, y, z, and time in this case. If we let V of x, y, z equal the mechanical potential energy, then the force would be minus the gradient of V. And one more. If we let phi of x, y, z equal electrostatic potential, then the electric field is defined as minus the gradient of the electrostatic potential. So we see in these two examples that the gradient is used to define important aspects, important functions in quantum mechanics like force and electric field. Let's do two examples. Let's define V of x, y, z to be this. Then force, which we said was the gradient of V, so force is going to equal minus the gradient of V, and that is going to be the partials. Right, the gradient is defined as the partial with respect to x times I plus partial with respect to y of j, or times j, plus partial with respect to z of k. So in calculating that, we get kx, ky, kz are constants, so we get this x minus out front. Derivative of this is just x, so it's x k sub x I plus y k sub y j plus z k sub z k. So there's the force, if we know that this is the mechanical potential energy. On this last blackboard for this video, let's define what we call the divergence, div, of a function a, and that is going to be defined as the gradient dotted with a. So let's see what that means. Remember, the gradient is going to be, the gradient, if we write it in vector form, is partial f partial x. Gradient, is just an operator, so it's partial x, partial y, partial z, and we're dotting that with a, which we can write in vector form as a sub x, comma a sub y, comma a sub z. And if we dot this together, it's product, but since all of these parts of the gradient are operators, it's these operators acting on these components. And so what we get is this. We get partial a sub x, partial x, plus, remember the dot product adds the product of the components together, partial a sub y, partial y, plus partial a sub z, partial z. So this concludes this first video on Chapter 13. In subsequent videos on Chapter 13, we'll look at some more example and or homework problems in this section.